So let's consider now a ring of charge. For sake of simplicity, I'm going to assume that this ring of charge is uniformly charged with a total charge Q. So if I want to create a charge density, I would take that charge Q and spread it over the length of the ring. The circumference of the ring is 2 pi times the radius of the ring. Let's take R to be the radius of the ring. Now the reason I do this is because I'm going to start looking at small arc elements of the ring. So I would like to use the method of symmetry to do this problem. To find the electric field at point P is my aim. The point P being on the axis perpendicular to the ring. Now let me just emphasize that this is the only problem we can do with the amount of mathematics that we know at UP2 level. If you take a point slightly off the axis, this becomes a graduate school problem. It's very difficult. So let's take a small element here, dq, and the corresponding mirror element, dq prime, and see what kind of electric fields they exert at the point P. Now since the whole ring is one kind of charge, I'm going to assume it to be a positive charge. The electric field due to dq is going to be in this direction, and the electric field due to dq prime is going to be in this direction. I'll call them dE and dE prime respectively. As you can see, the components along the xy plane will cancel out, leaving us with just a component along the z-axis that add up together. Let's define this angle to be theta, and let's call the height of point P above the xy plane simply z. This is r. So by the Pythagorean theorem, that is just the square root of r squared plus z squared. That angle is theta, as is that angle. So we can write our electric field at point P, dE at P. Let me also draw it. That's how it would look. It's 2 times dE sine theta. Now dE for a point charge is k dq over r squared. So that's 2 times k dq over r squared times sine theta, which by trigonometry is z divided by r. So looks like everything is going really simply here. Let's put everything in. Now dq by ds is lambda, which in this case is lambda naught. So that tells me that dq is lambda naught times ds. Now we have to use the arc geometry. I've already used the variable theta, so I'm out of luck there. The arc geometry can be used with a different variable. I'm going to call this variable phi, d phi. So if you look at this arc of a circle, the relationship between ds and d phi is that ds equals r d phi. Okay, I can do one more thing, and that is to take lambda naught to be q over 2 pi r. Times r d phi. You observe that r cancels out, and so dq is q over 2 pi times d phi. Well, that's an interesting interpretation of the charge. It is the total charge in a small sector d phi is a charge per unit angle times the angle, which makes sense because charge equals charge per unit angle times angle. Anyway, let's substitute everything in here. I'll get dEP equals 2 times k q over 2 pi z over r cubed d phi. If you integrate it, you will get the full electric field. But because we have used the mirror elements, we can only integrate it from phi equal to 0 to phi equal to pi, not over phi equal to 2 pi, because we have already used, for every element we have used the mirror element. We can only go halfway around the circle. So this is phi equal to 0 to phi equal to pi of dEP. Now this is one of the easiest integrals you could ever do, because everything here is constant. K is just Coulomb's constant, Q is constant, 2 pi, I can cancel that 2 there. Z is constant because we are at a fixed height. R is also constant, so bring everything out, and I'm just left with the integral of d phi. Integral of d phi is just phi. So, and the integral of phi, and the phi between limits of 0 and pi is just pi. So I'm left with kq over pi z over r cubed times pi, which cancels nicely with this pi. So in this fashion, I've got one of the nicest results you could imagine, and that is the electric field due to a point charge, due to a ring of charge, a certain distance z above the ring's plane along the ring's axis. Now r here is r squared plus z squared, so let's put that back to the power 3/2. So that is the result we have obtained. The direction is, of course, along the k hat direction, so we can, if you like, make this a vector equation. I was a little hesitant to do this because there are 2 k's here. This is Coulomb's constant and that is the unit vector k. Please don't confuse them. Well, with this result, can we go one step further? Can we use this result as a stepping stone to a new problem? How about trying to find the charge on an infinite sheet? Now, how are we going to do this? Using just this result. The technique is a very interesting one. What we're going to do is, so far this ring has been considered to have 0 thickness. We're going to cheat a little bit. We're going to imagine a ring with some thickness. And we're going to say as long as the thickness remains small, we can use this result that we had for a ring with 0 thickness and get the same field if we have a ring with some definite thickness. So let the thickness of this ring be dr, and let the radius of this ring be little r. We are still interested in that same point P, located a distance z above this ring. The question is, how can we use the result we just obtained for a ring and expand it to the entire 2-dimensional plane? We can no longer use the density of lambda naught. We have to use a 2-dimensional type of density. I'm going to draw the infinite plane that I seek to build using rings. So if you like to think about it, if you slice an onion, you're going to find these little rings, little onion rings, and the onion is going to be built by stacking those rings. Now imagine an infinite onion, and when you cut the infinite onion, you're going to see these rings radiating from the middle of the onion all the way to infinity. So that's a lot of onions. What you're going to do now is to find a way to get the charge of the entire plane worked into this. We're going to do that by using the concept of surface charge density. Surface charge density sigma, in this case it's sigma naught because it's a constant density, is defined as the charge dq over the area element dA. Now the area of this ring, because this ring has got thickness, dA is 2 pi r, which is circumference, times thickness, dr. So we can find dq by multiplying it with sigma naught times 2 pi r dr. So what I'm going to do is this. I'm going to play a little shell game. I'll substitute for q dq. I'll substitute for capital R, little r. Z I'll leave alone. Also, I won't worry about the vectors. Let me do all that. So I end up with the electric field, which I'll call now dE, because this is the electric field just due to that onion ring. So dE at point P, the new dE at point P, is going to be k times dq z over r squared plus z squared to the power 3/2. Now dq is all of this. So that's going to be k times sigma naught 2 pi, I'll put the z first, r dr over r squared plus z squared to the power 3/2. The total electric field is got by integrating over all the values of r. You're going from r equal to 0 all the way to r equal to infinity. So the total electric field EP is going to be, I can certainly take out some of these constant things, 2 pi sigma naught and k come outside. Z is also a constant. And then I have to go from 0 to infinity, r dr divided by r squared plus z squared to the power 3/2. Now this is not a very difficult integral. In fact, U substitution will do the trick. I know that you've studied U substitution, but I'd like to teach you something slightly a little bit cooler than a U substitution, and that's a U squared substitution, which I'm sure you did not learn. So here's the U squared substitution. Instead of saying U equal to something, I'm going to say U squared equal to R squared plus Z squared, because then I don't have to deal with square roots ever again. If I differentiate both sides, I'm going to get 2U du equals 2R dr. Remember that R is the variable, not Z. So basically this tells me that R dr is the same as U du. Also, when R equal to 0, U equal to Z. And when R equal to infinity, U is still equal to infinity. So the limits are going to be from Z to infinity for U. So I'm going to get E sub P equal to 2 pi sigma naught kz integral from U equal to Z to infinity U du divided by, now remember, since I've called U squared equal to R squared plus Z squared, this is going to be U squared to the power 3/2. U squared to the power 3/2 is simply U cubed. So that is 2 pi sigma naught kz, the integral from z to infinity du by U squared. The integral of 1 over U squared is negative 1 over U. So that's just negative 2 pi sigma naught kz over U z to infinity. Now at infinity, if u goes to infinity, the denominator becomes very large, the whole thing goes to 0. So I only have to worry about the lower limit. But the lower limit comes with a negative sign. So the negative sign there and the negative sign here cancels out. And when I put z in the denominator for the lower limit, that z and the numerator z cancel out. So I just end up with 2 pi sigma naught times the Coulomb constant k. This is a very important result. It is so important that I'm going to restate it, even though I have not introduced the following constant. I'm going to restate it in terms of a new constant. Let me define k equals 1 over 4 pi epsilon naught. The Coulomb constant I'm writing as 1 over 4 pi times epsilon naught. I will talk more about epsilon naught next week when I discuss Gauss's law. But for now, just think of it as a new constant. So if I write this in terms of the new constant epsilon naught, the 4 pi and the 2 pi cancel out to give me sigma naught over 2 epsilon naught. Now this example has been done in the course of 15 or so minutes in a very complicated fashion. We went from the ring of charge, and then we fudged around between the ring and the onion slice, and then we went from there to the infinite plane, and we got this result. I just want to write it in this form because next week when we study Gauss's law, you can get this result in less than 2 lines. That shows the power of Gauss's law. But last comment is that this is constant. It doesn't matter how far you are from the sheet. The electric field is the same. And that's a pretty amazing result.